Swayam Prabha. Digital India. Educated India.
Welcome to the class. Now we are going to see some examples on Rankine cycle with reheat, or the example which are related with steam power plant with reheating arrangement. So the first example reads that the Rankine cycle based steam power plant has an ideal reheater. Boiler outlet conditions are 15 megapascal and 600 degrees Celsius. Condenser pressure is 10 kilopascal. The moisture content at the exit of the low pressure turbine is 0.896. That means dryness fraction is given as 0.896. The example reads that a Rankine cycle based steam power plant has an ideal reheater. Boiler outlet conditions are 15 megapascal and 600 degree Celsius. Condenser pressure is 10 kilopascal. The dryness fraction at the exit of low pressure turbine is 0.896. Find reheat pressure and thermal efficiency. Consider the temperature after reheating or after the reheat is to be 600 degree Celsius. So let us draw first the reheat cycle and then name all the corners. This is So this is how the Rankine cycle with reheat is. Let us correlate it with given things. So in the given things we are told that P2 is equal to P3 is equal to 15 megapascal. T3 is said as 600 degrees Celsius. We are also told that T5 is also 600 degree Celsius. We are told that P6 is equal to P1 is equal to 10 kPa, and we have X6 as 0.896. We are supposed to find out what is P4, what is P5. So this is what first thing which we have to find out. So for that we can first find out entropy S6. And so we know S6 can be found out by saying that it is S1 plus X6 into SFG. S1 can be found out as 10 kPa liquid saturation entropy, which is 0.6492 plus 0.896 into SFG, which is 7.4996. So this gives us S6 as 7.3688 kilojoule per kg Kelvin. So this is the entropy at the exit of the low pressure turbine. We know this is low pressure turbine and this is high pressure turbine. Having said this, we can say that S6 is equal to S5, which is 7.3688. Now we also know T5 is equal to 600 degree Celsius. So basically here we can go into the steam table, in the superheated part of the steam table, and see 600 degree Celsius corresponding to different pressures, and find out a pressure and corresponding to temperature 600 degree Celsius, which would have entropy 7.3688. So that pressure becomes the basically the pressure P5. So we can do that. Similarly, knowing this, we can find out H6. H6 is equal to H1 plus X6 into HFG. So it is 191.81 plus 0.896 into 2392.1, and we get H6 as 2335.1 kilojoule per kg. So we can get this from these known quantities. However, we would have to go as suggested for in the steam table. So pressure P5 can be found out from steam table at 600 degrees Celsius, and S has 7.3688. So we get this with P5, and this P5 remains as 4 megapascal. So here at the same state we can find an H5 which turns out to be 3674.9 kilojoule per kg. So now we know P5, we know everything at state 5. Enthalpy also is known to us. So now we will proceed with the other things. So for that we can know first H1, and H1 for us is here 191.81 kilojoule per kg, and then we should know V1, and this is 0.001010 meter cube per kg. So we can find out pump work as new one into P2 minus P1. So 001010 into P2 is 15 into 10 to the power 3 minus 10. So this gives in kilojoule per kg. So pump work in kilojoule per kg turns out to be 15.14 kilojoule per kg. Now we can find out H2 is equal to H1 plus pump work. So we have 191.81 plus 15.14, and then this turns out to be 206.95 kilojoule per kg. Now we know H2. We can find out H3, and H3 we can find out from steam table, and we can go to the 15 megapascal superheated condition, find out the enthalpy and entropy corresponding to 600 degree Celsius. So H3 at this state will be 3583.1 kilojoule per kg. S3 at the same location 6.6796 kilojoule per kg Kelvin. So we can now find out the state 4. Here we should also remember S4 is equal to S3, but we know P4 is equal to 4 megapascal, which is basically P5. So again we will go to the steam table, we will look into the 4 megapascal case and find out what is the temperature at which if we can get the entropy as S3. Okay, so it turns out that we can find out the temperature, and this temperature can be the saturation temperature. The 0.4 can be inside the dome or 0.4 can be outside the dome. If 0.4 is inside the dome, then we would have to find out the dryness fraction for 0.4. If it is outside the dome, then we know that it will have dryness fraction 1. So here we will get H4 is equal to 3155.0, since T4 turns out to be 375.5 degrees Celsius. So we can go ahead and do the next calculations, which are for Q in is equal to, we have to remember that we are adding heat in two places. We are adding heat here in the boiler and in the reheater. So it is H1, it is basically H3 minus H2 plus H5 minus H4. So Q in is equal to 3583.1 minus 206.95 plus 3674.9 minus 3155, and we get Q in as 3896.1 kilojoule per kg. Similarly, we can find out Q out, and Q out is H6 minus H1. H6 is 2335.1 minus 191.81. So we have Q out is equal to 2143.3 kilojoule per kg. So cycle efficiency is equal to 1 minus Q out upon Q in, so which is 1 minus 2143.3 divided by 3896.1. So cycle efficiency become 0.45, which is 45%. So this is how we would have to solve the example. Here we have to keep one point in mind, that in the example, in some cases we would not be given, as in this example, the pressure, which is the reheat pressure, and we have to find out reheat pressure from the entropy equal condition at S6 is equal to S5 and S4 is equal to S3. So using these conditions we can find out location of 0.4 by one match, which is S6 is equal to S5. We can identify the pressure, and by making other match, which is S3 is equal to S4, we will get its temperature known, or maybe along with temperature we can also know whether the point is inside the dome or outside the dome. We will go ahead with the next example. It reads that steam power plant operates between boiler conditions of 3 megapascal and 400 degrees Celsius and condenser pressure of 10 kilopascal. Okay. After expansion in high pressure turbine till 0.6 megapascal, steam is reheated till 400 degree Celsius. Find out cycle efficiency and quality at the exit of low pressure turbine. In this example, we are given with reheat pressure, so we don't have to find it out. But what is not known to us is the dryness fraction at the exit of the low pressure turbine. So this is 1, 2, 3, 4, 5, 6. So given is P3 is equal to P2 is equal to 3 megapascal. Then T3 is equal to T5 is equal to 400 degrees Celsius. P1 is equal to P6 is equal to 10 kPa, and then P5 is equal to P4 is equal to 0.6 megapascal. Then here we will go ahead with our classical known things first. H1 can be known corresponding to 10 kilopascal, which is 191.83 kilojoule per kg. V1 is known as 001010 meter cube per kg, and then we can find out pump work, which is V1 into P2 minus P1, which is 001010 into 3 kilopascal minus 10 kilopascal, and the unit will be in kilojoule per kg, which is 3.0199 kilojoule per kg. So we know H2 is equal to H1 plus WP 191.83 plus 3.0199, and then we get H2 as 194.85 kilojoule per kg. So we can find out still H3, which is corresponding to 400 degrees Celsius, 3 megapascal. We have to go into the superheated part of the steam table and find out H3, and H3 is 3230.9 kilojoule per kg. Immediately we will note down S3, and S3 is 6.9212 kilojoule per kg Kelvin. Now we know that P4 is equal to 0.6 megapascal, and we also know that S4 is equal to S3. Now we know S3, so we have to go into the steam table. First we have to see what is the saturation entropy of vapor at 0.6 megapascal, and that we have to compare with 6.9212. If 6.9212 is more than the saturation entropy of vapor, then we have to go into the superheated part and match the pressure and temperature. Rather, for the 0.6 megapascal we have to find out the temperature, which would give the entropy this. If we find out that saturation entropy for 4 is, or saturation entropy for 0.6 megapascal is greater than S4, then we find out X4, which is dryness fraction at 4. Okay, since from that we can basically equate its entropy with S3. So in the present case we will have basically Sg, which is saturation vapor entropy is less than S3. So we have to find out in superheated part, and we get T4 is equal to 190.97 degrees Celsius. Since we know P4 is equal to 0.6 megapascal, and then at that location we can find out H4, and H4 turns out to be 2829.63 kilojoule per kg. So now we can go in P4, basically P5 as 0.6 megapascal and T5 as 400 degrees Celsius, and find out H5, and H5 gives us the value 3270.3 kilojoule per kg. but at the same moment we will note down S5, and S5 is 7.7079 kilojoule per kg Kelvin. So now we can find out what is the state at 6. Since we know S6 is equal to S5 and then which is equal to S1 plus X6 into SFG. We have already noted down S1 for the 10 kilopascal case. We would also know XFG at 10 kilopascal, and then we already know S5 which is 7.7079, and this gives us X6 is equal to S5 minus S1 divided by SFG. So it is 7.7079 minus 0.6493 divided by SFG is basically SG minus SF. So SG is 8.1502 minus 0.6493. This gives us X6 as 0.941. This is the dryness fraction at state 6. So we can find out H6 also by saying it is H1 plus X6 into HFG, which is 191.83 plus 0.941 into HFG, and this HFG is HF minus HG, which is 2584.7 minus 191.83, and this gives us value as 2443.52 kilojoule per kg. Using these numbers we can proceed and find out rest of the parameters. So we can find out Q in. Again there is heat addition in two places. One is H3 minus H2 into boiler and H5 minus H4 in the reheater. So Q in is equal to 3230.9 minus 194.85 plus H5 is 3270.3 minus 2829.63. So this is H4. So from that we can get Q in as 3476.72 kilojoule per kg. Similarly we can find out Q out, and Q out is equal to H6 minus H1. So it is 2443.52 minus 191.83. So we get Q out is equal to 2251.69 kilojoule per kg. So we can find out efficiency as 1 minus Q out upon Q in. So it is 1 minus 2251.69 divided by Q in is 3476.72, and we get efficiency as 35.23%. So in this example we were supposed to find out two things. One is cycle efficiency and quality at the exit. Here the question quality refers to finding out dryness fraction at the exit of the low pressure turbine, which we found out. Okay, so this is how we have to work with the example of reheater, where either we will be given with the reheat pressure, and we have to find out the conditions at the exit of the turbine, or we might be given conditions at the exit of the turbine, and then we would have to find out the reheat condition. So this is the way we would solve the examples on reheater. Thank you.